Good morning everyone, welcome to today's class. Today we will discuss about the Hilbert spaces and Hilbertian norms. It is in second chapter. So Hilbert spaces, basic notations and examples we will see. Let H be a linear space over C means a set of complex numbers with a given complex valued function of two variables. We will say it as inner product xy from H cross H to C, which has the following properties. This we have discussed in a linear algebra class. So we are discussing a linear algebra class detailedly. So with these properties, first property is linearity with respect to the first argument. First argument means whatever coming in this first place. In this case, this is the first argument. So linearity in the first argument means ax1 plus bx2 inner product with y means it is equivalent to ax1 inner product with y plus bx2 inner product with y. Now you can take this constant terms, that is a scalar terms a and b, outside from the first one. Okay. Second one, conjugate linearity in second variable, that is xy inner product of x comma is the x comma y bar is equal to inner product of yx. And the third condition, non-negativeness, that is inner product of xx is always greater than or equal to 0, and inner product of xx is equal to 0 if and only if x equal to 0. Now such a function is called an inner product or a scalar product. I repeat, first condition is linearity with respect to the first argument. Second one, conjugate linearity, that is xy conjugate is equal to inner product of yx. Next, non-negativeness. Non-negativeness means norm of inner product of xx is always greater than or equal to 0, and inner product of xx equal to 0 if and only if x equal to 0. Now from condition 2, we have x comma a y1 plus b y2 is a bar, that is a conjugate xy1 plus b conjugate xy2. Okay, this may will say that conjugate linearity. Now for proof, consider this quantity x comma a y1 plus b y2. Now this can be written as the conjugate, that is we are using the second property. So this property we are using and we are rewriting this as a y1 plus b y2 comma x conjugate. Okay, now expansion can be taken out, that is equal to a y1 plus x plus inner product of b y2 x all conjugate. So that can be split up into a y x inner product of a y y1 comma x conjugate plus inner product of b y2 comma x. Now from this, using the second one, again you can write this equal to a conjugate into y1 comma x conjugate, and this can be written as b conjugate into y2 comma x conjugate. Now again using the conjugate idea, next stage you can write this equal to inner product of x1 y1, and this can be written as inner product of x comma y2. That's the result. We will consider the inner product of x with x. Inner product of x with x, and when you raise it, you're taking the positive square root, means you will get a quantity. That quantity we are naming as p of x. Now p of x is a norm. We will write p of x is equal to norm x. So you have studied in your linear algebra class during your first sem. Now some examples of inner product. First one is in multiples of complex numbers. Like inner product defined as inner product of xy is equal to coordinate wise addition, but in that coordinate we are taking y's conjugate, that is b1 conjugate, b2 conjugate, right now. So sigma 1 to n ai bi conjugate, where x equal to ai from 1 to n and y equal to bi from 1 to n. That is x is equal to a1 a2 extra an and y is equal to b1 b2 extra bn, where ai comma bi belongs to c. Then its inner product is defined as a1 b1 conjugate plus a2 b2 conjugate plus etc plus an bn conjugate. Now this inner product is an inner product that we want to prove. Now if your f is equal to r, then this inner product is also called dot product. That means whenever your field is a real number, then b1 conjugate, b2 conjugate, everything will become b1, b2, b3. So for finding the inner product of xy, it is enough to find the sum a1 b1 plus a2 b2 plus a3 b3 plus extra plus an bn. That is nothing but our dot product. Now in L2, going for one more example. In L2, the inner product of xy is equal to sigma I equal to 1 to infinity ai bi conjugate, ai bi conjugate. In that case, first of all we will say that this is well defined, since you take two elements x and y from your L2, so it should be sequences. Then xy. Inner product of xy is defined as sigma I equal to 1 to infinity ai bi conjugate. Since sigma, we want to prove that this inner product this is an inner product. So first we want to prove that this is well defined. So we take what is modulus of sigma ai bi bar, that is less than or equal to sigma ai square raised to 1 by 2 sigma bi square raised to 1 by 2. This we called by Holder's inequality by taking p and q is equal to 1 by 2. This quantity is less than infinity. That means it is a finite quantity, since xy belongs to L2, which implies this inner product is well defined. In this space, I will take a third example. The space C2 of AB, right? The inner product of F is, you know that C2 of AB means set of all continuous functions defined from closed level AB to set of real numbers. If you're writing 2 means in that the norm is 2, right? So inner product of Fg is defined as integral a to b f of t g of t conjugate into dt. Now again, using Holder's inequality for p and q is equal to 2, again we will get this quantity is now equal to modulus of ff, inner product of ff, into modulus of inner product of gg. And I am leaving this for you to check whether this will satisfy all the conditions of inner product. So inner product, first we want to check positive non-negativeness condition. Next is condition linearity in first argument, and second one linearity in or conjugate symmetry. Okay, these three conditions you want to check for example 1, 2 and 3. Next topic is Cauchy-Schwarz inequality and Hilbertian norm. So first of all, let us see what is Cauchy-Schwarz inequality. So theorem 2.1.1, for all vectors x, y in a linear space H with inner product is given inner product, the following inequality called the Cauchy-Schwarz inequality is true. That is, mod of inner product of xy is less than or equal to inner product of xs raised to 1 by 2 dot inner product of yy raised to 1 by 2. Okay, we will prove this. We have put this in another way in your linear algebra class. Here we are proving it like this. First you consider inner product of xs raised to 1 by 2. Call that as norm of x or p of x. And we have the idea norm of alpha plus or minus beta all square is equal to norm of alpha square plus or minus 2 times real part of alpha inner product of alpha with beta plus norm of beta square. Now consider an element x minus lambda y and take its inner product with that itself. This inner product of x minus lambda I and x minus lambda y, which is always greater than or equal to 0. That is, when you find this means you get norm of x minus lambda y square. So norm of x minus lambda y square is greater than or equal to 0. Now expanding this using the square idea, we will get norm x square minus, since it is minus sign, minus 2 times real part of inner product of x with lambda y plus norm of lambda y square. And this quantity is greater than or equal to 0. Now that is norm x square minus 2 times real part of, I'm writing this in the reverse way. That is, when you are taking the conjugate also, real part of a complex number and its conjugate are the same. So I can write real part of lambda y comma x plus norm of lambda y square. That is norm x square minus 2 times real part of, I can take this lambda outside. So lambda into inner product of yx plus, from this I can take mod lambda square. So mod lambda square into norm y square. That is, we have assumed that norm of x is equal to p of x. So this can be replaced with p of x square. So p of x square minus 2 times real part of lambda into inner product of yx plus, here again I can use for mod norm y square as py square. So mod lambda square into py square is greater than or equal to 0. Calling this as equation 1. Now assume inner product of xy is not equal to 0. Assume inner product of xy not equal to 0. Now we can define lambda as p of x square by inner product of yx. P of lambda as p of x square by inner product of yx. Now substituting this in your equation 1, we will get p of x square minus 2 times real part of, instead of lambda I am having px square by inner product of yx with inner product yx plus px raised to 4, since it's containing mod lambda square, px raised to 4 by inner product of yx square into py square, which is greater than or equal to 0. That is px square minus 2 times See here, this will get cancelled. We have assumed that this is not equal to 0. So that will get cancelled. You'll get 2 times real part of px square. Px square already a real number. So it doesn't contain any imaginary part. So real part means that itself. Minus 2 times p of x square plus here px raised to 4 as it is by more inner product of yx square as it is, this term as it is, and this term is greater than or equal to 0. See here, px square minus 2px square. So you can simplify it. We will get minus px square plus px raised to 4 by inner product of yx square into py square is greater than or equal to 0. So take minus px square to this side. We will get px raised to 4 by inner product of yx square into py square is greater than or equal to px square. That is, again, px raised to 4 into py square. This quantity can be taken this side. Px square into inner product of yx square. Now dividing equation 2 with px square, we will get here inner product of yx square is less than or equal to, here you will get px square will get cancelled, so 1 px square, so px square into py square is px square plus px square into py square is greater than or equal to yx square. That is, yx square is same as inner product of xy square. So this can be written as the modulus of xy inner product of xy is less than or equal to, this side again everything is positive or greater than 0. So here we are having inner product of xx raised to 1 by 2 inner product of y raised to 1 by 2. So this is the Cauchy-Schwarz inequality. With this I'm stopping here. So if you're having any doubt, means you can ask. To now means in second chapter, when you examine your syllabus, you may come across that your first unit is over. So second chapter onwards, starting your second unit. So first unit was very small. So study well. We'll have some internals after that. Okay, after this part is over, I will start some internal. Okay, thank you.